Okay? Then what would be the other way to write the same expression?
So ये समझ में नहीं आ सकता.
That I am defining a map J that takes input this and gives output this actually. That's it. So it takes this input and gives this output. Within a minute, when you're going to take, for example, n equal to 3 or 2, you will see that this flipping of vectors means something. It's really the rotation actually. I'm going to tell you that what it means. Okay, so at the moment I'm just mathematically want to simplify this expression. So I want to write this h of u using j. So can you guess something?
Derivative.
Derivative what?
So this का derivative लेंगे, so partial derivative.
Here's the thing. Can I say h of u is that you take the gradient of the u in 2k. So it's like partial u by partial x1, partial u by partial x2, and partial u by partial x2k. And substitute into the j. Isn't it? Okay, so what is gradient of u? Partial u by partial x1 and partial u by partial x2 up to the partial u by partial xn, and I'm substituting into the j. So what will happen? The j is doing nothing, it's just flipping.
So partial derivatives.
So flipping, so whatever input you give me, just flip the components and this.
Yes.
So a Hamiltonian field is like this actually. Okay, so that's a way to write simply Hamiltonian field actually. Okay. For example, if you take n equal to 2, okay, take n equal to 2. What would be h of u? So h of u is going to be j of gradient of u, which is partial u by partial x1 and partial u by partial x2, and this would be what? Minus partial u by partial x2 and partial u by partial x1. If you want to interpret this in 2 dimensions actually, so imagine I have a map 1, 2 here and I'm substituting into the 2. So what is happening with the map? It's going to be negative 2, 1. So where is going to be negative 2? So I'm going to have, so 1, 2 is here. So
Minus 2, 1.
okay, just 1 moment. So this is 1 and this is like 2. So x is going to be negative 2. So negative 2 is here and 1. So this would be the negative 1. So somehow I was at, say, this point and I kind of reached at this point. Okay. You can also treat it as that you are rotating. So this is like doing a kind of a rotation with certain angle actually. Okay, so the point is being rotated into the certain angle. So j is what? So j is taking a point and it gives it a certain rotation actually. Would be interesting to ask with what angle it's being rotating.
So the rotation is predefined.
What do you mean by that?
I mean, the rotation within J is defined. We have already defined the rotation within J.
We have already defined it. क्या हो गया इनमें यार? Rotation between?
So just हम J जो है, वो U पर apply कर रहे हैं. वो rotation
J is being applied on a point on R2K. R2 से R2 में ले जा रहा है point, या R4 से R4 में.
और वो rotations जो है वो constant rotations से वो define की गई है J में.
Yes. It's taken from R2 to R2. So in classical mechanics, this guy is of very much importance. We're going to do a course on classical mechanics also in the 6th semester or maybe 5th semester. So what I would like to do? I would like to do this. By the way, J is rotation by pi by 2 degrees. It's a 90 degree rotation. Okay? So think about it. If you take a point on x-axis, say 1, 0, what are you going to get? 0, 1. Where is 0, 1? On y-axis. Okay? You can really see that this is like a 90 degree rotation. Okay? ठीक है जी? Okay. Now let's observe something interesting. Let's say compute, so take h of u, okay, and take the first component of the h of u, okay, and differentiate it. Okay? Differentiate it with respect to, for example, first component. So in other words, so let's call this component as h1. Let's call this component as h2. Okay. So if I, for example, compute the derivative, say, of h1 with respect to, say, y, okay, yeah, x2, इसको xy रखते हैं, इसको ये y और x होता है, ऐसे ही होगा नहीं, this will be x and y, and this would be y and x. ठीक है जी? So if I take this, you know, h1, which is h1, and I differentiate it with respect to y. So the partial h1 by partial y, okay, and so what would be this guy? So this is going to be minus partial, you know, partial 2u by partial y2, and partial, for example, h2 by partial x is partial 2u by partial x2. ठीक हो गया? And now I'm asking that compute their sum. So what would be their sum, or maybe their difference? So partial h2 by, say, partial y minus partial h1 by partial x. So it's going to be partial 2u by partial y2 plus partial 2u by partial x2, and we give this quantity a name. It's called the Laplacian of the u. Okay? Laplacian of the u. Maybe I can give this direction. Can you think of what this quantity is? ये quantity क्या है? Any guess about it?
2% डेरिवेटिव का फर्क है।
2% derivatives का?
फर्क है।
तो वो तो नजर आ रहा है। Anything else? If I ask you from the perspective of, say, curl, gradient, and divergence, what is it? It is actually. ये क्या चीज?
So अगर एक फंक्शन को एक दफा पार्शियली डेरिवेट करेंगे अलग अलग से, तो वो ग्रेडियंट के बराबर होता है। तो यहाँ पर दो बार कर रहे हैं तो
So it's like it's the divergence of the gradient. Think about it. So divergence of the gradient. So what is the del u? So partial u by partial x, and partial u by partial y. Okay. And what would be the divergence of this gradient x? Okay. I compute phi of that. So here's the thing. Here's the thing. What would be the divergence of h of u? h of u की divergence क्या होगी? क्या करना है?
सर पता नहीं क्या काम कर रहे थे लेकिन अभी क्या कर रहे हैं?
ठीक है? What would be the divergence of h of u? How do you compute divergence? So you take this, and differentiate it, for example, first with respect to x and with respect to y. So you're going to get what? You're going to get 0. Why the divergence of this entire process is 0?
क्योंकि हम पहले y के रेस्पेक्ट और उसकी
चलो
पार्शियल
वो तो mathematically हो गया ना. I can see that you can calculate derivatives and you can subtract.
इंटर भी हो रही है और आउट भी हो रही है.
So roughly what we are doing is that, like, this vector field is taking points and just reflecting them, rotating them with the 90 degree. Okay, rotating them with the 90 degree. It's not throwing them away. You see it? It's just making the rotations in the points. So when you pick a thing and you keep on rotating it, you are not spreading it. You're not throwing it away. You're not, kind of having the divergence actually. It's just really the rotation. So you expect it to be divergence free. Okay. This is one thing. Anyway, so if you compute divergence, you're going to get this. This guy, in other words, if you compute the derivatives of it, but with respect to the opposite variables, you get this actually. And this is called a Laplace equation, a Laplace operator. Partial 2u by partial x2 and partial 2u by partial y. Okay, this is called the Laplace operator. This Laplace operator. Okay. This can also be seen as, we can really prove that if you take the divergence of u, gradient of u, so it's going to be what? Partial u by partial x and partial u by partial y. Okay? And compute its divergence. Compute its divergence. So what would be the divergence of the gradient? So it's like you have this del and you want to compute the del of this partial u by partial x and partial u by partial y. So what would be the divergence of it? So then partial 2u by partial x2 plus partial 2u by partial y2. It's going to be really Laplace operator. So Laplace operator can be seen as, really divergence of the gradient. Okay? Divergence of gradient. So कभी इसके लिए this symbol is also used, actually we call it del square. Okay? We call it del square. What is the point of doing all that? Let's get to the class.
सर ये gradient field को हम कर्व कर रहे हैं, रोटेट कर रहे हैं, उस पे कर्व ऑपरेटर ऑपरेट कर रहे हैं. Gradient field.
So you are saying that, okay, you have the gradient, okay, it's like you have the flash anyway, and you want to know that how much, of this linear thing, okay, whatever that is diverging out. Because gradient बजाते खुद भी एक vector field ही है, okay? So it is going to be some vector field. And you say, what is the divergence of that some vector field?
सर वो इसके मुताबिक तो 0 हो गया.
नहीं, वो इसका, okay, so here's the thing. Yes, इसकी जो divergence है, that would be 0. Okay. But here, since I wanted to introduce this new notation, and I want to, kind of grasp it out of, or take it out of this, what you call Hamiltonian operator, you can treat this as an independent quantity. Okay? So I'm not calculating the divergence of the j of the gradient. So divergence of the j of the gradient is 0, but the divergence of the gradient is not necessarily 0 actually. ठीक? So it will be an operator and we are getting in the name Laplace operator. ठीक है? Let me come to the crux of all this. So with this bit of mathematics, you can have very interesting conclusion. Now I want to ask a question. When h of u, the Hamiltonian of u, is going to be irrotational, कब होगा irrotational? When it will be irrotational?
J को हम define करेंगे दूसरे तरीके से.
कैसे?
J mapping. तब हो सकता है सर. J को हमने इस तरह से define किया हुआ है कि इनकी positions vector components की switch हो रही है positions. अगर J को किसी और तरीके से define करें, इसमें rotation ना लाएं, ये हो सकता है.
अभी भी हो सकता है. अभी भी हो सकता है.
वहाँ पे एंगल 0 रखते हैं, रोटेशन एंगल.
So you are not moving it, sir. Everything is static. Freeze हो गया. So what you should do with the h of u? You're gonna say h of u is irrotational. Here's an interesting thing. H of u is irrotational if and only if. Can I say and think about it? Why this must be true? If u satisfies Laplace equation, ठीक है? Tell u equal to 0. Why this must be true? Rotationality का
वो constant होंगे और वो डेरिवेटिव लेंगे तो ये हो जाएगा.
why this must be? Think about it. Look a bit. What is the meaning of irrotationality? Okay. Let me write a quick proof of it. H of u is what? In 2 dimension. So I'm in dimension 2, obviously. Dimension. H of u is this. So minus partial u by partial y and partial u by partial x. So when this is irrotational,
The पहले component का partial derivative लें with respect to x is same as the partial derivative of the second term with respect to y. सर अगर
पहले का with respect to y and second का with respect to x.
सर यहाँ पे सर पहले y लिखा हुआ है.
Y
हाँ. इसका with respect to x.
X लेंगे.
x नहीं.
नहीं सर.
Think about it. So just keep remind that definition in your head actually. J.
Partial derivative of ith component of f with respect to j and the jth
So it's ith ना. I का मतलब 1 है.
Yes sir.
और j क्या हो सकता है?
2
1 तो नहीं हो सकता.
सही है.
ठीक है. So this is true if and only if. ठीक है. You're going to say the partial derivative of y of the first component is equal to the partial derivative with respect to x of the second component. है क्या नहीं? ठीक है. So what does this mean? So you're going to have the second order partial derivative of the y and you have a negative sign of it and take it to another side. So wouldn't that be same as okay, wouldn't that be same as Laplace of u equal to 0? So Hamiltonian is rotational. If what happens? Laplace of u equal to 0. Think about it. If you differentiate it partial u by partial to u by partial y and partial to u by partial x2, you take this on other side, the other side becomes Laplace u and that's equal to 0. Okay? This is one of the
सर मतलब ये कह रहे हैं कि जो हैमिल्टोनियन है सर उसका कर्ल 0 है तो हमारा जो Laplace होगा वो भी 0 होगा इसका Laplace of u.
So you would satisfy this Laplace equation. Okay. So there are two things. This operator is called Laplace operator, and u satisfies Laplace equation. Okay. In other words, this equation is called Laplace equation. It's a very interesting kind of an equation. You will learn it afterwards. Okay. Okay. Now, if H is irrotational, what does this mean actually? If H is irrotational, so what conclusion you can get from Poincare lemma? So what does Poincare lemma tell you? So if you have an irrotational vector field, then something interesting happens. What does something interesting happen? Let me say one more thing. So those functions which satisfy Laplace equation, we call them harmonic. So U is harmonic. Okay? It's like a musical thing actually. You see there is music. Okay? So H of U would be irrotational if and only if U is harmonic. So what is the definition of U being harmonic? That it satisfies the Laplace equation actually. Here's a question. What does this tell you about क्या बताता है आपको ये conclusion about the Hamiltonian field? So the Poincare lemma tells you that if a vector field is rotational, then you can find the potential of it. It must be gradient field. Okay, it must be a gradient field. Now, if H is H of U is irrotational, then we can find a V, okay, and that V is going to be what? H of U equal to the gradient of the V. Okay, H of U must be equal to the gradient of the V. V has a very interesting name. Okay, what is H of U? So let's get into. Let's explore it a bit more. So H of U is minus partial u by partial y and partial u by partial x. Okay. And the gradient of V would be partial v by partial x and partial v by partial y. And if you compare them, then you're going to get minus partial u by partial y equal to minus partial v by partial x. Okay, and what? The partial u by partial x is equal to partial v by partial y. These equations are called Cauchy-Riemann equations. Okay? These equations are called Cauchy-Riemann equations. Here's the thing. If the Cauchy-Riemann equations are satisfied, then H of U is gradient and hence rotational. Or if it is rotational, Cauchy-Riemann equations must be satisfied. Okay? This guy V moreover, this guy V is called the harmonic conjugate of the U vector. Conjugate of the U. Okay? It's called the harmonic conjugate of the U. Shall I summarize what we did? And we will see that what an interesting thing we have done actually. Apparently, just this jumble of equations actually making no sense, just going here and there. You know, see that all going to make sense actually. So I have now in dimension 2 and I have Hamiltonian vector field. And it's going to be rotational. So if it is Laplace, it satisfies Euler satisfies Laplace equation. In other words, U is a harmonic function. So if U satisfies Laplace equation, in other words, h of U is irrotational. Poincaré lemma tells me that then I can find a V which is going to satisfy the same regularity, okay, such that h of U can be written as the gradient of V. And I can rewrite it and explore it. So h of U is this and gradient of V is this. So this is kind of a if h of U of the Hamiltonian is irrotational, then these equations must be satisfied. It's like a necessary condition. Okay. One thing, if U is harmonic, my claim is V is also harmonic actually. Can you help me out in deducing that V must also be harmonic? And if Q harmonic होगा, so I want to show V is harmonic. In other words, I want to show the Laplace operator. If I compute the Laplace operator for V, it must be 0. What would be the Laplace operator for V? How can I compute it? So I need to compute partial 2V by partial x2 and partial 2V by partial y. Right? What would be partial 2V by partial x2? I know U is harmonic and the partial V by partial x is partial U by partial y. So can I say this would be same as partial V by partial x of minus partial U by partial y. You have partial U by partial y and partial, you have the partial U by partial x. Okay? And since the function is C2 class, okay, partial 2U by partial x, partial y, partial 2U by partial y, partial x. So if your function is smooth, they must be there. So the harmonic conjugate must be harmonic as well. Let's do one example and let's see what interesting curves that we get. Take U equal to x square minus y square. Take U equal to x square minus y square. Is it harmonic? How can I know U is harmonic? You just need to check, does it satisfy the Laplace equation? So you can see that if I differentiate it 2 times with respect to x is going to give me 2, minus with respect to y is going to give me 2. So you're going to get 0. Can I find its harmonic conjugate? I can find its harmonic conjugate. So Cauchy-Riemann equation can help us. I know U, so I can find V. As I know, U is known to me. So what would be the harmonic conjugate? So partial V by partial x is equal to, from Cauchy-Riemann equations, minus partial U by partial y. So it's going to be 2y. Okay? And V is going to be y square plus some function depending on x. Okay? It's going to be some function depending on x because you're integrating with respect to x. So how can I find this unknown function? Differentiate it. So if I differentiate it with respect to, for example, say x or y, say y, so I'm going to get 2y. No, I need to differentiate it with respect to x.
दूसरा कंपोनेंट करा है
दूसरा कंपोनेंट इस्तेमाल मैं इसी में से कैसे डिड्यूस करें? So okay, really silly thing. So this is not going to be y square, it's going to be 2xy. मैं तो सो रहा हूँ, आप मुझसे ज़्यादा सो रहे हैं. So it's going to be 2xy. It's going to be 2xy. ठीक है. So now I would like to know what? I would like to find this g of x. So let's compute partial v by partial x or partial y, for example.